These last two, I'm not sure.
Gonna take that moles
Mhm.
and divide, so you're gonna, it's a ratio between those.
Yeah.
And then you divide by the smallest of them.
Oh, okay, gotcha.
So how are you doing?
I'm here. Okay, folks, I'm gonna go ahead and get started. So the first thing is just some quick announcements. Number one, a few of you owe some labs from last week because of the fact that you didn't get it finished in lab. So that's due. The second announcement is that the lab this week is a lab lecture. Announcement is you do have a quiz that's due at 11:59 p.m. today. The fourth announcement, and I do need to check what that quiz is over. I want to say I did it correctly. Let me check. The fourth announcement is you do have a homework that's going to be over ionic compounds. And the last announcement is exam number 2 is a week from today. So exam number 2 will go through the naming of ionic compounds and the formulas of ionic compounds. It will not include covalent molecules. It won't include the acids, which we're to discuss on Thursday. Any questions before I begin? So the majority of the exam on Tuesday of next week is about electron configurations. Whether they're the full electron configuration, the noble gas electron configuration, the box diagram, quantum numbers from the box diagram, or and then that would be for elements that follow the normal pattern, anomalies, and ions. And then we will get into, trying to think, my brain is, I think it gets into the, all of the atomic trends and calculation of Z effective. And then finally getting into the ions themselves and learning your ions and then being able to name them or give the formula, and then also working with ionic compounds. Okay, so on Thursday of last week, I started an introduction to the ions. I focused on the elemental ions at that time. Your metals will always form cations. There are some metals that the cation that they form is always going to be the same, meaning that it's always going to have the exact same charge, no matter where you find that cation. That was group 1, group 2, silver, zinc, cadmium, aluminum, gallium, and indium. Those particular metals, they will always form a ion with the exact same charge, no matter where you find the ion. All of the rest of the metals have charges that can vary, and because they do have charges that can vary, we do have to name them slightly differently, in that when we name an ion of a metal whose charge can vary, we have to name the metal, and then we have to give the charges of Roman numeral in parentheses. As far as your nonmetals and metalloids, they can form anions, and we talked about the fact that group 15 nonmetals and metalloids form an anion of a -3. Group 16 nonmetals and metalloids form an anion of a group of -2, and group 17 nonmetals form an anion of a -1. And as far as naming the anions, it is always the root of the name, but it ends in IDE to distinguish it between the anion and the neutral element. Anions always have IDE. Today, what we're going to do is we're going to get into the polyatomic ions. Polyatomic ions, the term literally means, poly means many, so many atom ions. The majority of these many atom ions are going to involve oxygen as the second element in the ion. And those are the ones that I can give you at least to some degree, I can give you a way to help you memorize those. Now, folks, even though I'm going to give you some trends in the ions, I cannot give you trends for all of the ions. Some of them you're just going to have to learn. And so you have that huge list that I gave you, and you're going to have to see which ones fit the trends that I'm about to discuss and which ones don't. The ones that don't fit the trend, you're just going to have to memorize, because I can't give you a way to help you memorize them. Now, what I'm going to be working with, I did have posted a document, whoops, wrong thing, that looks like this. And this is what I'm going to be working with. I'm going to be going over it though, so that hopefully I can explain what is in it. But if you want to have that document pulled up instead of starting from scratch, you would be able to do so. So that is up to you. It is also in last week's folder on Blackboard if you don't have the printed copy. But I'm actually going to write it from scratch because I think it helps me to slow down. Otherwise, I might talk rather quickly. So we're going to begin. First of all, what I'm going to be describing specifically are called oxyanions or oxyanions, however you want to say it. Basically, these are going to be polyatomics. that consist of oxygen and another element. And I'm actually going to talk about only period 2 and period 3. Because once I get to period 3, if you understand period 3, you understand oxyions in period 4, 5, 6, and so on. So I find that if we can get the basics, you won't have as many to memorize. But okay, so I'm going to start with the period 2 oxyions. Now, with period 2, to make the oxyion of boron, it's going to be BO3, 3 minus. Carbon, it's CO3, 2 minus. And nitrogen, it is NO3 minus. So what is the first trend you recognize? Okay, so one of the trends is the charge magnitude drops by 1. Starting with boron. When I talk about magnitude, I'm talking about the numerical value associated with the charge, not the sign of the charge. So yes, it goes 3, 2, 1. Well, we'll get to that. But what other thing about just the formula do you notice? They always have 3 oxygens. Now, these are the 8. So bore 8, carbon 8, and nitrate. So folks, the 8s of period 2 all have 3 oxygens, and their charge drops by 1, starting with boron. Now, group 15 is known as a family of 2. And what that means is you can have nitrate, and then if it's a family of 2, the second one will be called nitrite. Now, to go from nitrate to nitrite with respect to the formula, the only thing that changes is the number of oxygens, and it drops by 1. to go from 8 to 8, the only thing that changes in the formula is the number of oxygens. The charge does not change. It's just the number of oxygens, yes. No, I'm talking family of 2 means there's only going to be 1 8 and 1 8. Okay. Next, we're going to move into period 3 through 7 trends because they're all the same. In other words, period 2 is a little bit different. It's going to be treated slightly different than all of the rest of them. Okay. So when we get into this, well, first of all, let me go back a moment on some of these. You had phosphide, which we discussed on Thursday, sulfide, and chloride. Ide means that it's an anion of an element. Now for our polyatomics. What do you notice? The 8, or let's call it the largest 8 in the case because of the family of 4 there. They will all have 4 oxygens. Now for our family of 2, which was group 15 and group 16, what else do you notice? Actually, for really 16, 17, or 15, 16, and 17. They do decrease in charge, but what else? But more importantly, the charge is the same as that of the anion, as that of the elemental anion. I say that because most people know from previous experience that phosphide is a 3 minus, that sulfide is a 2 minus. Well, the fact that their polyatomics have the exact same charge will help you in knowing their charges as well. In other words, the phosphorus anions in general, phosphorus anions are 3 minus. Sulfur anions are 2 minus. It doesn't matter whether they're an oxyion or an elemental ion. They always have the same charge. That should help in memorizing the charges. If you realize that all of the ions have the same charge. Now again, group 15 and group 16 are going to be families of 2. And the only thing that's going to change again is the number of oxygens. It's going to drop by 1. So folks, why I say that is I don't memorize my ites. I don't memorize phosphite. I don't memorize sulfite. Because I know the trend, since they're in a family of 2, to get to the 8, all I got to do is remove an oxygen from the 8. That helps in the memory work if you understand that trend. Folks, if you have the sheet of paper in front of you and you look at the ions for arsenic, selenium, and tellurium on that sheet of paper, you're going to see the exact same trends. So you don't have to memorize how arsenic's going to behave. You don't have to memorize how selenium's going to behave. You don't have to memorize how tellurium's going to behave. Because if you know how phosphorus behaves, you know how arsenic behaves. If you know how sulfur behaves, you know how selenium and tellurium behave. Because their behavior is always the same, because they're in a family of 2 in the same group. That means there's a lot of stuff I don't memorize. Nitrate to nitrite, I don't memorize the ites in any of it, because to go from an 8 to an 8, all I do is drop an oxygen. I don't memorize arsenic, selenium, and tellurium, because I know how the element above those particular elements behave. And therefore arsenic's going to behave just like phosphorus, selenium and tellurium are going to behave just like sulfur. That's going to reduce your memory work if you know that concept, those trends. Because otherwise you've got about 88 polyatomic ions to memorize. Now, I said at the top of this that chlorine is in a family of 4. What a family of 4 means is that it can drop the number of oxygens 4 times. What a family of 4 means is that it can drop the number of oxygens 4 times. Now, as far as our polyatomic ions are concerned, when naming them, we really only have two options. It's either going to be the 8 or it's going to be the ite. However, no two ions can have the same name. So we cannot have two chlorates. We cannot have two chlorides. So that is when we bring in some prefixes. The prefix for the largest is going to be per. So ClO4 minus is perchlorate. The prefix for the smallest is hypo. So that is going to be ClO minus is hypochlorite. That's how we distinguish the fact that we have a family of 4. Now, folks, just like I didn't have to memorize arsenic, selenium, and tellurium because I knew arsenic's going to behave like phosphorus, and I know selenium and tellurium are going to behave like sulfur. You don't have to memorize bromine and iodine because they're going to behave just like chlorine. So the trends thus far, period 2, you got 3 oxygens. It drops by 1 magnitude on each charge to get the 8s. Period 3 through 7, the 8 will always have 4 oxygens to start. But in period 3 through 7, specifically for groups 15 through 17, their 8, their oxy ion, has the exact same charge as their elemental ion. And then I don't memorize my ites. I just know that in periods 15 through 16, to go from 8 to ite, I drop an oxygen. That's all I change. And in period 17, because it's a family of 4, that means I drop it 4 times, or well, 3 more times. And the largest 2 will be 8, the smallest 2 will be ite as far as numbers of oxygens. But we have to distinguish the big one with the per and the smallest one with the hypo. Okay, now there are some additional trends. That's the big set of trends. That will help a lot if you know those trends. The additional trends are what happens when you add hydrogen to an oxy ion. One of the reasons hydrogen stands above lithium, sodium, potassium, and rubidium, and so on, is because one of hydrogen's possible charges is an H plus. Now, when you take that H plus and combine it with something like PO4 3 minus, To figure out the charge that's going to result on HPO4, well, that's a +1 from the hydrogen, a -3 from the phosphate, giving it a total of a -2. So now it's a 2- charge. And to name this, we now add the word hydrogen because we added a hydrogen. So we add the word hydrogen to the polyatomic that we worked with. So HPO4 2- becomes hydrogen phosphate. Now, you could also add 2 hydrogens to PO4 3- so that you have H2PO4, and the charge will be a +2 from the 2 hydrogens, a -3 from the phosphate, giving it a total of a -1 charge. Now the prefix for 2 is di. So this is dihydrogen phosphate. So do you think I memorized hydrogen phosphate and dihydrogen phosphate, or hydrogen sulfate and hydrogen sulfite, or anything like that? No, because I know hydrogen's a +1 and I can figure out the charge. I'm trying to help you with the memory work because there is a 88, right around 88 if I recall, or 80 something ions to memorize. That's a lot of ions. So I'm trying to help you figure it out rather than just having to memorize so many things. Now, there is one more trend. It's something we've actually already seen, but it is anytime there are 4 oxygens with a -1 charge, then the prefix will be per, and the suffix will be 8. We've already seen this in the ClO4 -1. You've got 4 oxygens, -1 charge. So that's why this one was perchlorate. But where you have not seen this is this one. By knowing the trend for oxygens, -1 charge, I didn't have to memorize it. It has to be permanganate. as I said at the beginning, I can't give you trends for everything. But if you know these trends, you know a lot of your ions. There are going to be some that I can't give you, like hydroxide, cyanide. I will give you one more that will help you. Oh, actually, this is just a term. If you see the term thio at the beginning, if you see the prefix thio, it means sulfur's been added. But really, as far as the majority, I cannot give you I can't, you're just gonna have to memorize some. But hopefully these trends help you memorize some of them. Questions?
We just read the entire list again.
It's just, if you know the trends, it helps a lot. You could go through and highlight just how many these 5 trends cover. And you would see that the amount in that 2-page list has greatly been reduced. In that 2-page list, I gave you names for the metal ions. Well, I've told you how to learn how to do those. You shouldn't have to memorize them. You just need to know group 1, group 2, silver, zinc, cadmium, aluminum, gallium, and indium are always the same charge. So they just get their name plus ion. And then all the rest of the metals, you've got to have the Roman numeral with. So you shouldn't be memorizing those. Your anions, yes, you should know that the elemental anions end in IDE, and that everybody in group 15 is a -3, everybody in group 16 is a -2, everybody in group 17 is a -1. What I specifically focused on today was ways to help you memorize the rest of that table, which are all of your polyatomic ions, to the best of my ability. Again, that list is on last week's folder. So now on that list, I did give you, there are some that I've given you 2 ways to name. I did that because I want to say that active learning sometimes will use the old naming rather than the IUPAC naming. What I describe in class with the name plus Roman numeral is the IUPAC naming. But sometimes they'll use the old naming, and so that's why I gave you that. The extras there is in case you come across Mercurus. What is Mercurus? It's Mercury 1. It's just there to let you know that they're the same thing. But on a test, I focus on IUPAC. Okay, so let's get into ionic compounds. Let's get into what it is all for. Ionic compounds contain ionic bonds. An ionic bond is the electrostatic attraction or magnetic attraction between a positively charged cation and a negatively charged anion. The number of cations and the number of anions in an ionic compound are equivalent to the number required to make a charge neutral compound. The number of each ion is shown as a subscript in the formula. The cation is always listed first. That's my shorthand notation for compound. Sorry about that. Yeah, CPD is my shorthand notation for compound. Okay, so what does this mean? Let's take the fact that I have calcium. Calcium is in group 2, so what is its charge? Two plus. And I want to combine that with chloride. If you think about it right now, you have a +2 from the calcium and a -1 from the chlorine. That gives you an overall charge of a +1. So it does not equal 0. So it's not in a 1-to-1 ratio because compounds must be charge neutral. The one in the lowest quantity is the negative charge. So we're going to add a second chlorine. When we do so, we have +2 from the calcium, and we now have -2 from the 2 chlorines. That gives us an overall charge of 0. So now it is charge neutral. So in order to make a compound with calcium and chlorine, you need 1 calcium and you need 2 chlorines. We illustrate the number we needed as subscripts for each element. In naming this compound, if you'll recall, calcium, because it is in group 2, it's always a +2. There's no question about it. So that would be calcium ion. And Cl- is the anion of an element, so it ends in IDE, so that's chloride. To get the name of the compound, you're going to simply combine the names of the ions without the word ion. So CaCl2 is calcium chloride. Let's look at another one. Let's go with these two ions. If you look at their overall charges, you have a +3 and you have a -2. That equals a +1. So since it does not equal 0, we are not at a, we don't have the correct amount. Right now, the anion is in the lowest quantity, so we're going to add another anion to it. When you do so, you have +3, and now because you have 2 sulfates, it's a -4. So that gives us a -1. So it's still not at charge neutral. So since the cation is in the lowest supply, we'll add another cation. So now we have +6 -4. That equals a +2. So it still does not equal a charge neutral compound. So we add another sulfate to this, and that will be +6 -6. So finally we do equal 0. So in other words, a compound that has Au3 plus and SO4 2- in it will require 2 Au3 pluses, and it will require 3 SO4s. Now, to indicate we need 3 of the polyatomic, you place the polyatomic in parentheses with the quantity needed outside the parentheses. You never, ever, ever change the formula of the polyatomic ion. If you need more than one of the polyatomic ion, you place that polyatomic ion in parentheses and the number needed outside. That way, basically you're saying, when you do this, you're saying, I need 3 of this entire unit. Is literally what that says. Now I'm going to show you an easier way to get to the formulas. This is just showing you why. They have to be charge neutral. Now to name this, gold is not one of the metals whose charge is always the same. So what does it need? Needs a Roman numeral telling me what the charge is. And I have a polyatomic of period 3 that has 4 oxygens. So what is its ending going to be? 8. So once I combine them, the formula's name is gold 3 sulfate. Questions?
don't they like account for like the number of sulfates you have? Like why is it not like go along the trial?
Okay. First of all, so why did we not include prefixes to tell us how many? Ionic compounds, other than those hydrates, do not have prefixes. And the reason for that is because ionic compounds will always be based off of the charges and it'll always come up to the lowest whole number ratio possible. So we don't need to know how many's there because that's the only formula you could have for gold-3 and sulfate. The only reason we use prefixes are when you can have more than one formula with the same elements, but you can't here because of the way ionic compounds work. This also could have been, I believe it's arum sulfate. Could have been the same thing, but again, I will be using the IUPAC naming. Okay, so what's an easier way to get to these formulas? The easier way to get to the formulas is cross, drop, simplify. And you got to remember that last step. So you're going to cross the magnitudes. Drop it on the opposite ion. As a subscript. And then simplify if needed. Basically, you will need to simplify if the subscripts dropped are divisible by any number but one. I'll typically just call it cross, drop, simplify, but I wanted to explain what you're crossing, dropping, and simplifying. So let's go back to that example of AU 3 plus, SO4 2 minus. I'm going to take the 3 of the gold and I am going to cross and drop it on my polyatomic ion. I am going to take the 2 of the sulfate and I'm going to cross and drop it onto the gold. So on the gold, I dropped a 2. Whoops. On the sulfate, I dropped a 3. And they're not divisible by any number but 1. So that is the simplified version. If I have Ag and phosphate, first of all, what is the charge on silver? Do I know the charge on silver? It is a +1. It's always a +1. And the phosphate 8, it's a 3- because it's the same as phosphides would be. So I'm going to cross. There's a 1 here, even though it wasn't showing. I'm going to drop it onto the phosphate. I'm going to take the 3 of the phosphate and drop it onto the silver. So I'm going to have Ag 3 PO4. And since it's only 1, we don't have to put it in parentheses. You only have to put it in parentheses if it's more than 1. Because the parentheses says, is basically saying that polyatomic ion is a unit. And because silver is always a constant charge, this would simply be silver phosphate. Questions? Folks, if you don't know your ions, it's going to hurt. That's why in last week's folder, you also have a Quizlet for ions. You don't even have to build your own Quizlet or your own. I mean, if you want cards, you can, or you can use the Quizlet. Whatever works for you. Okay, so we've taken the name, basically we've started with the ions and gotten to the formula and the name. But yeah, you might have to go from ions to formula, but more likely you're going to go from the name to the formula. So if you go from name to formula, the very first thing you're going to do is you're going to translate the name to the appropriate ions. And then you do the cross, drop, simplify. So let's go with tin-2 nitride. The first thing I have to do is translate. I see a Roman numeral, so that's telling me what the charge is on the tin. It is a 2+. The other thing I recognize is I have the ending IDE. When the ending is IDE, what type of anion am I talking about? Element. So what is, do that. So what is the charge of a nitrogen anion? 3- because it's in group 15. So we've translated. Now we're going to cross, drop, and simplify if needed. So this is SN3N2. Let's look at another one. Let's look at chromium Vi oxide. I see a Roman numeral, so it must be telling me the charge on my metal, which is a 6 plus. Again, I spot the ending IDE, other than for a very select few. That means it's an anion of an element. So it's the anion of oxygen, which is a 2 minus. We're going to cross it. Well, we'll cross and drop. So on our chromium, we're putting a 2, on our oxygen, a 6. But this is where you have to remember the last piece, because ionic compound formulas are always in the smallest whole number ratio possible. Ionic compound formulas must be in the smallest whole number ratio possible. Since 2 and 6 are divisible by 2, we have to do so. So this formula would be CrO3. Questions about how to take names and go to formulas? Besides, you got to memorize all the ions.
But does it work across all of those? That works. Does that work for everything?
That works for all ionic compounds. Meaning there's a metal. As long as there's a metal, it works. Which I guess I should have put back there when we were talking about ionic compounds. You will recognize an ionic compound if it contains a metal. You will recognize it as an ionic compound if it contains a metal. If it does not contain a metal, it is not an ionic compound, and there are different rules. So you'll recognize it as an ionic compound if it contains a metal. Okay, so names to formulas really aren't overly bad, as long as you know the names of your ions. And who has, basically, names to formulas aren't bad if you know which metals always have a constant charge and what that charge is. And if you know the names of your anions. Ide, 90% of the time, is an element. Ate and ite will always be polyatomics. What is the toughest piece is to go from the formula to the name. For an ionic compound. Okay, so the ides that are not elements. There are 3. The 3 ides that are not elements are polyatomic ions. The first is CN minus is cyanide. The second OH minus is hydroxide. And the last is O2, 2 minus, which is peroxide. These are the only polyatomic ions that do not end in ate or ite that are anions. These are the only polyatomic ions that end in IDE, like the elemental anions. That's why I said 90% of the time it's an element, but these are the 3 exceptions. And yes, O2, 2 minus is what's in hydrogen peroxide or peroxide that you can buy from the store. Hydroxide is a particularly important one when we start talking about bases. So you will encounter these. You hopefully won't encounter cyanide since that is poisonous. But the other 2 will encounter. Okay, so formula to name is the toughest. The first thing you're going to do is ask yourself the question. Is the cation a metal whose charge is always the same or is it ammonium? Ammonium is the polyatomic ion NH4+. That's the first question you're asking yourself. If you answer yes to this question, then you will simply name the metal and you will name the anion. As a reminder, this is specifically group 1 is a +1, group 2 is a +2. Then we're talking about silver, cadmium, zinc, aluminum, gallium, and indium. Now, if you answer no to this question because it's not one of those metals, then you name the metal. You will indicate metal charge as a Roman numeral. And you will name the anion. Of this is the second part is the hard step because you're gonna have to calculate the charge. So let's just look at an example. Say I have Na2O. Following that flow chart. Is it a metal that always has the same charge? Yes, because sodium is in group 1. So we're going this way. So we simply are going to name the metal and name the anion. So that is sodium oxide. How about TiO2? Is the cation a metal that always has the same charge? In this particular case, no, because it's not one of these. It's not one of the ones in blue. So no. So I'm going to have to ultimately figure out what that charge is. So to do so, even though it's not shown, that means you have 1 titanium. And we're gonna assign, and you can assign any variable you want. You want a variable to titanium. That variable is saying, I don't know what the charge is, so I'm gonna give it a variable A for the charge right now. But do we know the charge on the oxygen? Yes, it's group 16. Group 16 is always a 2 minus. So what we have is we have 1 times A minus 2 times a -2. And because ionic compounds must be charged neutral, we set that equal to 0. So you have A minus 4 is equal to 0. A equals 4. So that titanium has a +4 charge. So this would be named titanium 4 oxide. You cannot just uncross, folks. I see a lot of students when we talked about how to go from the formula to from the ions down to the name or to the formula, we cross dropped it, but You can't just uncross because of that last step where you had to simplify. You can't just uncross it. There is a worksheet in this week's homework pile that is ionic compounds. I would suggest getting on all this memory work and practicing that worksheet. We will pick up with a few examples on Thursday, but then we're going to move on to covalent molecules, which will not be on the test. But I would suggest starting to practice this because this is one of those topics that you don't want to wait until Monday night to study. See you Thursday. No, there wasn't. I just forgot it.